Hi everyone, Mr. Lee here. In this video, we're going to go over rotational kinetic energy. Let's begin. So up on your screen, you should see two formulas. The first formula is just translational kinetic energy. This is just the kinetic energy of an object that is moving, which is 1/2 mass times the velocity squared. And right underneath of it is the rotational form of that formula, where Ke subscript r, or sometimes you might see me write it as Ke subscript ROT, is equal to 1/2 I omega squared, where I is rotational inertia, just like mass, and omega is rotational velocity. So the two formulas look almost identical, except one is for rotating objects and one is for the translational, or just a object that is moving in a straight line, basically. Okay, so let's take a deep dive into why we would use one or the other, or when we would use both. But let's back up a little bit. Let's go into the world of moving objects. So I'm going to give you two scenarios. Scenario one is what we're going to call a gliding scenario. Okay, and scenario two is going to be a rolling scenario. Now, the first scenario, where a gliding scenario, okay, let's say we had a object with no friction. Okay, so there's a surface with no friction, and we have a ball here. Now, what I want you to do is I want you to imagine that this ball is just gliding across this surface, and there's no friction. Now, this gliding is, there is no rotation. Okay, and it's important that there is no rotation here. So when this object just moves across the table, we say it just has a translational velocity, or just velocity for short. Okay, and what that means is that the center of mass, right there, it just moves across the surface. Now, we hardly ever really get to see this kind of stuff. Maybe like on ice, or if we were to throw an object in space, it would kind of look like this, where there's no rotation. But in the real world, not a lot of objects just glide like that. In the real world, a lot of objects roll. Now, there's a couple of very specific things that need to happen when we have rolling objects. Okay, one, you will often see on problems that we have rolling without slipping. Okay, and this is very, very, very important. Okay, rolling without slipping, and this in itself leads to more discussions, and we'll get into that later. Now, rolling in general is just what you would imagine if you were to have a ball and you were to kick the ball will roll, okay, along this surface. And in order for this to happen, there must be friction, okay, or some amount of friction. It could be like the tiniest amount of friction. Friction does exist. All right. Now, with this being said, we're going to go a little bit deeper into this, because that's the whole point of this video, this whole idea of rolling. There's a couple of things that you must know. The first one, the force of friction that acts on this object. So if I were to redraw this object, and I suggest that you do as well, I'm going to draw a little bit bigger. Okay, so if that's my object and this is the floor, when this object is on contact, or is making contact with the floor, I'm going to make this a little bit of a better circle. Okay, only at this point, okay, this is the only contact point. And only at that point will there be a force of friction. Okay, so friction exists only at that point. Now, let's go over what it means when we say rolling without slipping, by coming up with a definition of rolling with slipping. So if an object is rolling along the floor, there's no slipping. But if an object is rolling along the floor and there is slipping, so it's kind of like if you were to walk across the floor, and it's like there's like water on the floor, and you step on the water puddle, right? So instead of your foot moving backwards, your foot kind of slides forwards. Okay, so that's the definition of slipping. Another one that you can think about is, imagine a car. So I'm going to zoom out over here to do a quick little sketch. Normally, when you push the gas pedals on a car, the car just moves forward. But for certain circumstances, you might see some cars do this, like at the racetracks, where the tires spin in place, and usually like a lot of smoke and dust gets blowed up, right? But the tires are just rotating in place, but the car's not going anywhere. Okay, and so that right there is a example of rolling without, or rolling with slipping. So the car is rotating in place, but it's slipping because it's not pushing the car forward. Okay, all right. So when we say rolling without slipping, what we're saying is that it's just continually rolling, and it's not just gliding. You can think about gliding and slipping to be almost kind of the same thing. All right. All right. So with this being said, you need to also know this, that friction does no work, okay, on an object that rolls without slipping, because, okay, and we're gonna do a quick little review. All right, the formula for work is force times displacement. Okay, and if we're looking at the force of friction, so we say that there was no work done by friction, zero work done by friction, because the force of friction has no displacement. So what this means is that the force of friction is not pushing this point in any direction. When there is contact of that point on the floor, that point will not move forward or backward because of the force of friction. Okay, so the force of friction is not doing any work. Now, that's important because that actually ties in with the idea that there is no rolling without slipping. All right. Now, if we were to review what we just said, that point will not move forward or backward because of the force of friction, all right, what we have here is a very unique scenario. The force of friction that is happening is a static force of friction. Okay? Because if we were to look at that point when an object is rolling, if we were to freeze frame on that point is not moving. And that's kind of weird to say, because if this object was rolling forward, okay, let's say it's rolling in the forward direction, if we were to take a look at the object as a whole, we can say that this point up here, I'll indicate this with the orange dot, that point up there, that point on the object, let's say it's a ball, is moving forward. Okay, that point is moving forward, but this point right here, okay, where it's making contact, is not moving at all, okay, in this freeze frame. So here we can say there is a velocity. In fact, we can call that the tangential velocity, and here your velocity is 0. And that's kind of abstract to think, but that's how rolling happens. When you have one point that is not moving versus a point that is moving. So this point moves forward, okay, and we get this rotating motion. All right, now with that being said, let's go into the actual formula. Okay, so we're not going to review this whole idea of rolling without slipping, just so you know that rolling without slipping simply means that this object is rotating and is not rotating in place. Okay, for the next example. If we were to, a classic example is if we were to come up with a object that is, let's say, on top of a ramp. Okay, we have an object that is on top of a ramp, and this object rolls down the ramp without slipping. Okay, so the reason why we went into that giant tangent is so that we can say that now, and you should know what it means. This object rolls down, woo, right, and then it reaches the flat part and it rolls forward. All right, now what I want to do is I want to compare this current scenario versus a scenario that we looked at before where the object was not rolling, where this object just slides down the ramp or glides down the ramp. So here we have a rolling scenario, and here we have a sliding scenario or a gliding scenario where this object simply moves down the ramp, hits the bottom, and moves forward, where here the object is rolling. All right, now if we were to come up with the energy formula, we would say here at the top, the initial energy, versus down here at the bottom where we have final energy, we could write out the formula like this. The total mechanical energy initial is equal to the total mechanical energy final. Where initially at the top, we can say there is gravitational potential. So we say there is UG, okay, plus KE is equal to UG final plus KE final. Now you might be thinking to yourself, but Mr. Lee, at the top, isn't the object at rest? And you're right, the object is at rest. So my next line down, I'm going to get rid of all the energies that are 0. So at the top, we have gravitational potential, and that gravitational potential as it rolls down the ramp turns into kinetic energy final. Where at the very bottom, because it's not above a height of 0, we can say there is no gravitational potential energy. Okay, and then we can substitute in our formula of mgh is equal to 1/2 mv squared, right? And then we can solve the problem that way. So this is what we were used to before when we were doing the conservation of energy unit. Now let's switch it up. Now we have a rolling object. So what happens here is that your initial setup is going to be the same, right? You say that your initial mechanical energy is equal to your final mechanical energy. Okay, but what I'm going to do is I'm going to list off all of the different kinds of mechanical energy so that we can cancel them out later. So we say we start off with gravitational potential initial plus kinetic energy initial plus kinetic energy rotational initial is equal to gravitational energy final plus kinetic energy final plus kinetic energy rotational final. All right, so I'm going to zoom in on this equation here. All right, so when the object is at the top, it has only gravitational potential energy, and it's not sliding down. So we can say all of the kinetic energies are 0. We can say the kinetic energy initial is 0 because it's not moving. Okay, we can also say the kinetic energy rotational is 0 because in the beginning, it's not spinning, it's not rotating. So these are both 0. Now, at the bottom of the ramp, the potential energy becomes 0 because we have a height of 0, right? We reach the bottom. Now, at the bottom, it has two forms of energy, and we're about to dive into what those two forms are. Those two forms is the translational kinetic energy, and so what this means, I'm going to write it down, and so should you, is that the object is moving forward, and we have rotational kinetic energy. What that means is that it's spinning. So before we write those notes down, I'm going to come up with a formula here. We have UG initial is equal to kinetic energy final plus kinetic energy rotational final. Okay, now let's do a quick little definition check here. This kinetic energy is translational, and what that means is just moving forward or just moving in general. Right, it's just moving, and I'll say moving slash forward because that's what it's doing in our situation here. And for this one, kinetic energy rotational final, this is the rotational form of the energy, and what this means that it is rolling slash spinning. Okay, and so what this means is that some of the energy is taken from the initial gravitational potential to help it spin. So if we were to take a look at this scenario, right, I'm going to do a pretty solid line to say that we're messing around with numbers. Okay, so let's say we started off with 100 joules of gravitational potential energy. Okay, we have 100 joules of gravitational potential energy for both scenarios. Okay, we have 100 joules of gravitational potential energy. Now, for the scenario on the right, we can say that as long as there's no energy that is lost due to friction, all of that potential energy gets turned into kinetic energy, right? It's the conservation of energy. But here, it's not the same because some of this 100 goes into helping this move forward, and some of this 100 joules of potential energy helps it with spinning. So we can say, I'm just going to come up with numbers here, that some of it goes into helping it move forward. So let's just say 70 joules is meant for translation. So it's moving forward with 70 joules of kinetic energy and therefore 30 joules of rotational kinetic energy. Okay, so if I were to ask you which scenario A or B, okay, at the very end of the ramp, which object is moving faster, we will say scenario B is moving faster because it has a greater kinetic energy. Because in scenario A, some of that mechanical energy is used to cause this object to spin. All right. Now, another scenario that you will observe is a at-will machine problem or a pulley system. So let's do a quick little sketch of that. Now, in the previous example, we only had one object, but in this one, we're going to have multiple objects. Okay, so let's do object B, object A, and the pulley itself will be object C. All right, so let's say object B is, let's say they're all above a height. Let's say this right here, this dotted line is height of 0. Okay, and initially nothing is moving. Okay, everything is at rest. All right, but after a while, what happens is the object starts to move, and let's say C rotates clockwise, B lowers down, and A is rising up. Okay, So if we were to come up with a formula for this, all right, we're looking at the system as a whole. My suggestion to you is to individually parcel out the kinds of energy that each object has. Okay, so for example, we can say for object A, it has initial gravitational potential energy. Okay, and that's because it's above a height of A, or it's above a height of 0. And this initial potential energy, okay, the object is going to go up even more. So it has gravitational final potential energy, and it's also going to be moving. So it also has kinetic energy, right? And because the object is not rotating, we can say that it has no rotational kinetic energy. Now, what about object B? So for here, we can say, I'm just going to write this in with my arrows so that we have it for record. The gravitational potential energy increases, and the kinetic energy also increases because it's gonna move up, it's gonna speed up. All right. What about object B? So object B, it's above a height, right, of 0. So we say it has gravitational potential energy. Object B is falling though. So, but it's not at the floor. It's falling, but it still has gravitational potential energy because it's above a height 0, and it's also moving, so it has kinetic energy. So here we can say that the gravitational potential energy overall for this object, it decreased because the height lowered, but the kinetic energy, it increased, okay, because it went from no motion to some motion. All right, and for the last one, what about object C? So object C is a pulley and is above a height. Okay, so we can say it has gravitational potential energy, and after the system is released, it still has gravitational potential energy, but now it's rotating. So we can say it has kinetic energy rotation. Okay, because before it wasn't rotating and now it is rotating. So if we were to take a look at what's happening with the system, we can say that use this color, these two, the final potential energy, it didn't change, so it stays stagnant, but the rotational energy, it did increase. Okay, so here what we can see is that the overall energy of the system, if we were to solve this numerically, it'll all be conserved because we can say that there were no outside forces that did work on the system. But now we can see exactly where the energy went based on the numbers that we were given. So we can see the gravitational potential energy increase for scenario 1, and so did the kinetic energy. And the gravitational potential energy for scenario B decreased, but the kinetic energy increased. And we can say that there was also a rotation within the pulley, right? And so we can see how all of these together would add up overall for the energy of the system.